Now, having seen the two counting principles, the rule of sum and the rule of product, let's see a particular kind of problems that when we are applying the rule of sum, there is a mistake hidden. Let's say that we are trying to fill a box with solutions, and we observe that we can fill it either with solutions from A or by solutions of B, but we forget about the word exclusively. That when we apply the rule of sum, either we can fill it with objects from A or from B, but exclusively. And now we observe that there are some solutions in A and B that are common. So we have the following program that if we just add them up, then we'll add the solutions in A, and then we will add the solutions in B, and there are some solutions that are common and they have been counted twice. So the solution to this problem is rather easy. We will apply the inclusion-exclusion principle from set theory. And what we just do is that we will subtract the common elements once. The inclusion-exclusion principle says that the cardinality of the union of these two sets equals the cardinality of set A plus the cardinality of set B minus the cardinality of their intersection. Let's see this with an example. How many integers from 1 to 1000 are multiples of 2 or 3? So here is the problem that we said about that if we are begin to count, and let's say that A is the set of all the numbers that are multiples of 2. We can easily count them and observe that these are 500 numbers, and then we take the numbers that are multiples of 3. These are 333. And here is the problem, that there are some common elements. In example, number 6 is written 2 multiplied by 3, and this is a number that is a multiple of 2, and also it is a multiple of 3. So we have to count how many multiples of 2 and 3 are there, and these are multiples of 6, and the multiples of 6 is 166. So we use now the inclusion-exclusion principle. You noted that I'm not using the rule of sum, but the inclusion-exclusion principle. The multiples that are multiples of 2 or 3 are, and I'm adding the multiples of 2, the multiples of 3, and I'm subtracting the multiples of 6. Another powerful idea comes for enumeration by set theory again. When it is easier to compute the complement of what we need to count, then we may use subtraction. We use this theorem from set theory again, that the cardinality of a set equals the cardinality of the global set, the universal set, minus the cardinality of its complement. We will see exactly what this means by our two examples. Especially, we will use this property when the constraint has the form at least k, or we are counting something that has negation in it. Let's see these two very important examples. The first example says how many numbers from 100 to 999 that have at least 15 are there. So let's see how we would analyze this problem. We would say that you want basically a 3-digit number, and then we may think that we need at least 15. So you could have exactly 15, we would have 2 5s, or we could have 3 5s. So there are 3 distinct cases, and then we would go further by counting each cases of them. Now, this is a correct but rather difficult analysis when we can use the negation. See the solution. The opposite is the numbers that have no 5s. When we are negating a number that has at least in it, see this paradigm, I am saying here that I need at least 1 5. So I could have 1 5, 2 5s, 3 5s in this example, but I could have further if I had more positions. I could have 4 5s or 5 5s. So the solutions has all these cases. All these cases it could go further. But if I negate this thing, the only thing that is left is practically 0. So the opposite is the number that have no 5s. And you could use this idea if I tell you what's the opposite of at least 2. The opposite of at least 2 is at most 1, etc. So back to our exercise. The opposite is the numbers that have no 5s by the rule of product. This is a much easier problem. because I have just 3 spots, and these spots have now the obligation to be from 100 to 999, and there should be no 5 in them. So for the first spot, I can't have a 0 there, but I can't have a 5 also, so there are 8 available options. And then for the other 2 spots, there are 9 options, all digits except 5. Again, now all available numbers are 9 times 10 times 10. It's a total of 900. So if you see now my picture here, what I've counted is what you see in red. In set A, what I'm trying to count here, there's the number 545, let's say, a number that has at least one 5. But here, outside of A, there's the number 444, let's say, that has no 5s. So I know how many elements are in the universal set, these are 900, and I know how many elements are in the red set, this is the complement of A, and I know that there are 648 numbers. So the numbers that have at least one 5 are 900 minus 648, so they are 252. Let's see now our 14th example that is about counting something that has negation in it. He asks me how many numbers from 100 to 999 that are not multiples of 9 are there. So here I observe that he's asking me to count something that has not a property. And I'm thinking that maybe it would be easier to count the opposite of what he's asking me. The opposite is that I want the numbers that are multiples of 9. And indeed, this is a lot easier than the initial question. So I have 3-digit numbers. I want them to be multiples of 9, and I'm thinking about the definition of multiple. One number to be a multiple of 9 should be written in the form 9 times k, where k is an integer, and I observe that 9 times 12 is lowest number that is greater than 100, and again 9 times 111 is the highest number that is lower than 999. So the totality of them from 12 to 111 is exactly 100 numbers. All available numbers are 9 times 10 times as the previous exercise, so they are 900. And again, I'm going to count what I was asked as 900, the total ways, minus the opposite of these that I was asked, 100. So the total numbers from 100 to 999 that are not multiples of 9 are exactly 800. So this is a very important slide, and I want you to take away the 2 thoughts you got here. The first one is the rule of thumb may have this problem, the double counting of some solution. We will apply then the inclusion-exclusion principle. And then the second thought that in some cases it will be easier to count the opposite of what I'm asked to, especially the constraint at least k, and of course if I am asked to count something that has negation in it.